on those, you put the phantom on the floor and raise the two, the portable up to as high as they can go. And then you column it, you open it up and then you take the, exposure, and it tells you if it passes.
There. So any questions on your flat field phantom? Yep.
Is it not flat?
See how that comes to George? Yeah, it's
Like,
flat.
you see her in the bottom?
When they say flat field, they basically talking about the top. I mean, it's a thick piece of like, what is that, lead or aluminum, Mr. Fong?
Right, so it'll either be like aluminum or copper. And you'll just slot it there at the bottom of the collimator, and you expose the entire IR. And we've talked about flat fields before.
Bless you.
Correction.
Flat field
Right,
correction.
flat field correction, exactly. Right, so how do you test for flat fields? You would use this flat field phantom, right, to do your corrections, to do your calibrations.
So this part here, this flat part, that's the part that'll be like closest to the house. That's the part that you're sliding. So that's why they call it flat. All right, with some machines, you would do the calibration tests with the grids. These are grids that come out of the wall bucket. I have never done a flat field calibration test on the grid. We used to have to take the grid out. So it was just the IR that was being exposed, like Mr. Funk said. And we also had to do the calibration test on the sky plate or detector itself. Alright, so this is just the test that says whether or not if it passed or failed. Will most likely be with the medical physicist. We'll see.
So if it says like failed on that side, do you have to redo it or?
Yeah, so if it says fail, like right here, all of the tests pass. If it says fail, the medical physicist will repeat. They will repeat that.
So we do that or they do that?
They do this portion. This is
Okay.
what their image looks like. For us, when we do calibration, you'll just see, like, it'll look like a blank image, but actually it's the different density shades of gray. So that's what you're looking for the calibration.
Oh, so, sorry.
Mhm.
So just to point something else on these test results, you'll notice, for example, some of those results you have on the bottom half of that.
That's facial MTF.
Spatial MTF.
That MTL.
MTF, right? And then that bottom one, what is that?
That is contrast
The
and noise
contrast
ratio.
of noise.
That's the noise ratio, right?
Yes,
So,
that's what they come.
CNR.
that's right, so stuff we talked about, right? Here you see it in real life.
Yeah.
Alright, so this is the video, kinda like what Charo was talking about. Let's see this video one, please.
Best experience I had. Mr. George.
Someone?
Technical support.
Do we have to do it on the share screen?
This is a stick up.
Sweet or mint or something.
A pen?
You have something.
Yeah.
Mint or sweet or something.
Oh, something sweet. No, my lunch. Oh, yeah, I do. You know what? It depends. Do you want to go? I have a hot chocolate packet. You can go get some hot chocolate. I have like the mix. Do you want the mix?
But we won't go and get
Huh?
it. We will
Oh
get
yeah,
it.
you'd have to
We
go
will
get it. No, that's it. I didn't put that much in here.
Samantha, what if you do? Can you organize ready so that I
I will.
so that I have
You should have
enough?
told me, Jay. You should have told me.
No.
What is it? Oh, it's onion. Oh.
So that I have enough time here, because if it's too last minute, I'm not
I
that fast,
will.
I'm a little slow to do that.
I'll send it.
But right now, I'm not that I want to do those, I want to do the boot camp few questions.
Excuse me, sir.
But you think it's a good idea to do those?
What I'm gonna try to do at least a couple times a week, I would try to look over them because we don't know for sure. You know what could be on it? That potentially could be. I mean, it potentially could be.
I could
And you wouldn't want to miss. I mean, you wouldn't want to miss it a second time. Yeah.
But
Start by placing the detector in the calibration tray on the floor, away from any electrical.
Go through it anyway for the correction.
Set the source to image distance
Where's
as
it
close
right?
to 72
When
inches
you
as
time to go
possible.
over it again. Maybe, right, because he chooses.
Adjust the collimator blades to fully expose the detector. Insert the copper aluminum filter onto the collimator with the copper side facing the tube. Ensure that there is nothing in the bead. This video will demonstrate the process to perform a full calibration on the DRX Plus detector. From the main menu, select the Utilities button, Detector Calibration, and then select the detector you wish to calibrate. Select X-ray Full from the choices. Start by placing the detector in the calibration tray on the floor, away from any electrical equipment. Set the source to image distance as close to 72 inches as possible. Adjust the collimator blades to fully expose the detector. Insert the copper aluminum filter onto the collimator with the copper side facing the tube. Ensure that there is nothing in the beam path, such as a lead marker that may have been left on the detector. Press the Begin Calibration button to start the calibration process. This will be an 8-step process and will take approximately 20 minutes to complete. Several steps will require no interaction by the radiographer. When prompted, acquire an image using the Prep Expose button as normal. To save time, we will skip ahead to step 2. Step 2 will require the radiographer to capture 4 more exposures following the same sequence as step 1. Here
So,
too, we'll
tells you what
advance
we're doing
to
here.
step 3 to save some time.
Yeah, the good thing about these machines is it will actually go through each step with you and tell you what's the next step in the process.
Yeah, because it says step 2 right here, and then this changed.
Step 3 is an automated process and will require no interaction by the radiographer. Step 4 is also an automated process. Step 5 will require the radiographer to acquire 4 more exposures when prompted. Step 6 is another automated process. Step 7 will require the radiographer to acquire 4 more exposures when prompted. And then finally, step 8, which is the final step, requires no interaction by the user. During this step, the system is performing its final analysis. When the calibration is completed, the pop-up menu will appear with the pass-fail status of the detector. Select OK to close this window, then select the back button. Then select the main menu button.
Alright, so that's basically how a calibration test is done.
Can you say it in your own words, man? I didn't understand nothing. Can you say it in your own words? I didn't understand nothing, but was on.
Oh, nothing that was on the video.
What was it trying to tell us?
Today, I will demo the Carestream DRX Evolution Plus X-ray system. The DRX Evolution Plus is
Basically what it was trying to tell us is what I explained to you before. This was Carestream system. We have a Philips system, so that flat field, you will open up the collimators all the way, slide that flat field onto the 2000. and you'll make your series of exposures. It'll prompt you what to do because the test will go, it'll be on the monitor, so as you go along, it's gonna tell you exactly what it is that you need to do. That video was just an example of how a calibration test is done. Again, it's gonna vary because it depends on the machine that you have.
Company.
Yes. All right, so any questions on flat field? Y'all got company in the back.
Oh, hey, hey.
One more thing I do want to point out about this calibration. So in the video you saw, they mentioned that the calibration took 20 minutes, which is a considerable amount of time.
Yeah.
Anytime anyone dropped a cassette on any of the Carestream portables, we would have to go through that 20-minute calibration. I'm not very happy having to do a 20-minute calibration every time I come into the building because every evening someone dropped a cassette from the portables. So please take care of your equipment. Be nice to your equipment. If you need to do something to your cassettes or your IRs, don't balance it precariously with half of it hanging off a table, right? Or balance it where it's wobbling on your machine. Put it somewhere steady so that you don't drop it by accident and force me to do a 20-minute calibration.
Right.
Okay?
And also, remember that orange light I tell y'all about that's in the bottom right corner on the Philips machines in the x-ray rooms. When you see that blinking, that means it is time for the calibration test to be done. Do not ignore that. You will see text that will ignore it. Don't. The longer you let it go, that's the more you're gonna start seeing your images not come out quite how they're supposed to with the technique factors that you have set. So say for a chest x-ray, if you have 120 kV at, I'm gonna just say 2.5 mass, but that came out really, really dark, but that orange light in the corner is steady blinking. That means you have probably let that calibration test go too long. So it starts affecting your exposure factors.
So you have to have a QC person?
No, you do that.
But
You-
that's
you
an
can do
on
that.
the job training.
That's on the job.
Okay.
So when I explain to you, when you slide that flat field across the collimator light on the 2000, you can do that. You can do that yourself. But they'll train you, or supposed to train you on the job, or like I said, those manuals that you get from the manufacturer. The manuals tell you a step-by-step guide on what you need to do on how to do that calibration test. Okay. So any questions on the flat field phantom and calibration test? Alright, so the next step, the ACR, which is the American College of Radiology, and the American Association of Physicists in Medicine, they determine the frequency in which QC testing should be done. It has up here weekly for techs. Now that everything is digital, it is probably gonna be like every 2 to 3 months if it's the calibration test. If you're the QC tech, you may have some tests that you need to do, not every week, but more frequently than the calibration test. Weekly QC now mainly refers to, I know, mammal, of course, because there are weekly tests in mammal that you have to do. Alright, so for the medical physicists, this is how often they have to do all of these QC tests. Whenever you see a medical physicist coming into the department and they're doing their QC tests on the machine, it can possibly take almost the entire day for them to do that. So that means that x-ray room is out of service until they finish doing what they need to do. I would say at minimum 4 hours. That's at minimum. Okay, so one that sticks out, because pretty much the medical physicists will come in annually, which means once a year, to perform these QC tests. But collimation, they come every 6 months, semi-annual, to perform this test. And that's to make sure that your collimation is not misaligned. Okay? So any question on the frequency of how often the QC tests are done?
Who would I know on the record?
But red is most important. We leave it at that, because we got company in the back. Okay. So for filtration, filtration is the most important part of patient protection. Why? Please don't let Mr. Fong down, because he's in the back.
Takes away the
Because it filters out the
low
low
energy
energy
photons.
Stop it, Melody.
low
Stop.
energy X-rays.
Yes, so filtration is there in place to filter out the low energy X-rays, and it's to clean up your image. Clean up that scatter, clean up the noise on your image. Okay? So most states, if not all states, require at least 2.5 millimeters of aluminum for total filtration. Yes.
You wanna let Mr. Fong down?
Yes.
Wait, I couldn't read, what you
So we wanna let him down, we need an answer. Can't leave me alone. Ain't that right?
So there is no actual way to measure the filtration directly, so what the medical physicist does is they measure the half value layer of the HVL, of the X-ray beam. Alright, so the half value layer for X-ray is 3 to 5 millimeters of aluminum, and filtration, of course, is tested
Annually.
Thank you. Thank you. So this is an example of the filtration sets that they would use. This is different levels of thickness of aluminum. And although it's blurry, but on this side, this is kind of like a general formula that the medical physicists would use. There are set numbers that they already have in place from at the time the machine was installed, or if it was majorly repaired, and they will use those numbers to plug into the formula. And no, y'all don't have to know this. That's just FYI.
Just background information.
It sure is,
Appreciate it.
because we got company in the back.
Well, we still appreciate it.
Filtration examples. So look how much clearer this picture is versus this picture to the right when you use filtration.
Take the bag out.
So you see more detail, it's a sharper image, and it's not noisy, it's not cloudy, so you can see why filtration is important. And which patient do you think is getting the most amount of scatter radiation?
Right.
The unfiltered.
Oh, yeah,
Yep.
yeah.
So for collimation, the most important thing that you need to remember is the misalignment must not exceed plus or minus 2% of the SID. And the way they test this is, you see these dots on the outside, right here? If the collimation is exceeding these two dots here in the corner, meaning they're outside of these 4 squares and they're on the edge, that means your collimator needs to be readjusted. That's for the medical physicist to do. Okay?
Plus or minus 2%, that's the 2 lines. That's in the box.
This right here is your plus or minus, the ones inside of the box. Yeah. So if your collimator is ranging outside where these dots are, then that means it's misaligned, and they have to adjust the collimation. So with these boxes, you have a negative side and you have a positive side. So the circles that are within each of these boxes, you cannot go outside of that. Your plus or minus 2%. Okay? I did have a video, but that's too much to go through and we're moving on. I'm trying to save time. For PBL, positive beam, limiting collimators, that's basically your automatic collimators that's on your X-ray machine. So when you put those detectors inside of the table and you hear the machine make that noise, zip, 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 it's automatically collimated. Okay? So that's what PBL is. And the X-ray beam from PBL should not extend past the IR unless you put it in override mode. So what is override mode?
That's the key, right? Okay.
Yep. So focal spot size. So focal spot size helps with your spatial resolution. So it's the ability for small objects to have high subject contrast and for your ability to see more detail on your image. So anytime you get new equipment or if your X-ray tube is replaced, you must install the new focal spot, and the medical physicist must come in to measure that focal spot. All right. So there's 3 tools that the medical physicist will use to measure focal spot size. One is the pinhole camera. All you need to know is that it's difficult to use and it uses an excessive amount of X-ray exposure.
Because they've got to get a certain amount of photons to actually reach through that tiny
Well,
hole.
what the physicist does is they set different exposure factors. So the key is right here. This is the little pinhole,
Mhm.
which is like right here.
Oh,
So they have to make sure that that light goes directly through this little pinhole right here.
so it's not the little PVC. Wow.
Mhm.
Okay.
And what they do is they set the X-ray tube up. This aperture is set in the middle, so they'll measure from the X-ray tube to the lead sheet with the light beaming through the pinhole, and then they'll measure from the X-ray tube all the way to your actual IR. And they make several exposures.
How long does that take? Like approximately?
I have never been in the room when you do it. Yeah, but it takes a minute. Yeah, it takes a while. And they have to keep adjusting the light
Mhm.
to make sure that the light is still actually going through that little pinhole. That's why it's difficult to use. Alright, the next one is the star pattern. So this one is a little bit easier to use, but it has limitations. You can only measure focal spot sizes from 0.1 to 0.3 millimeters. And basically this test is used to measure like the blurring region around the focal spot size. So this is kind of an example of what the star test pattern looks like. And the next one is the slit camera. So this is the one that medical physicists now mainly use because it's easier to use. All you do is just take this little aperture, put it in between the tube and your IR. All you have to do is make 2 exposures, one at a perpendicular angle, one at a parallel angle, and it gives them the measurement for their focal spot. So this one is much easier than the pinhole.
So it's just 2 exposures
2 exposures.
at like 90 degrees to each other.
Yeah. Alright, so KVP calibration. So if you ever notice that big gray box or white box or whatever it is in the X-ray room, that's your generator. That's what generates your KVP. So that has to be calibrated as well every year. And when the medical physicist does their calibration, they want to make sure that it's within the range of plus or minus 10% of the indicated KVP. So if they're testing 120 KVP, they want to make sure that the range stays within that 10%, plus or minus 10% range.
So you
Split camera? This the camera is used to measure the focal spot size. So it's on, they keep it on the base. You see the base here. This is the slit camera itself. This is what it looks like up close. So basically what you do is you set this base on the table. Or you set your, you'll set your IR on the table. Set the base next to the IR on the table, you can extend this, this piece here, cause it does move. And you'll extend it over the IR, you have your tube above, and the medical physicist will measure at a parallel angle with one exposure, perpendicular angle at another exposure. And that's to measure, that's how they measure the focal spot size. I don't know calculations, every calculation is different. This is just basically how they use the slit camera to measure focal spot size, or one of the ways they use to measure the focal spot size. But guess what all you need to know from this slide? Alright, any questions on the KVP calibration?
So theoretically, if you're shooting at, let's say, 80 kVp, you could be shooting anywhere between 88 and like 10% under, even if you set it at 80.
So 10% below or 10% above? Yeah, that's your range. To still try to get the same optimal image.
And how does that affect our like math whenever we're trying to like increase or decrease the contrast? Like if we thought we were shooting at 80, but it's really at 88.
Well, that's why they do this test, to
Oh.
make sure that it stays within range.
Okay.
You won't do that. This is all medical physicists now that's
Okay.
doing this.
Cool.
Yes. Mhm. So for your exposure time accuracy or your AEC, and what does AEC stand for? So this is AEC is designed for the constant optical density regardless of tissue thickness. So if you set your AEC, let's say if you're doing an abdominal x-ray, or let's say if you're doing a tip fill, if you use the AEC, you still should get the optimal density, no matter the thickness of the body part. Your exposure time accuracy will be between plus or minus 5% of any of the exposure times that are greater than 10 milliseconds. And if your AEC fails, the exposure should terminate at either 6 seconds or 600 max.
Okay.
So if you hear the exposure going for a really, really long time, that means your AEC is out of whack.
By that point, like, and you know your exposure is going to be off, you know that the patient has received a lot of mass. Do you repeat it? Like,
Not in that room, I would grab another machine and shut
yeah,
that
because
room down.
that machine
Yeah.
would be hot.
Exactly. Yep. So exposure linearity, this is the ability to produce constant radiation at various MA and exposure times. So meaning no matter what my MA or exposure time is, I should still be able to produce the constant radiation output. And that's the combination of MA and exposure times, and they should produce the same mass value. So, for instance, you have an exposure time of 1,000, and you have your MA at 10. So 1,000 times 10, it gives you 10,000, which is your 10 mass. So all of these combinations, if the medical physicist is doing the test, he uses these different combinations, it should give you in the ballpark of 10 mass.
Is this also within a percentage? Or is this just like it has to be this way? Like the other ones were within 10%, is this within like 1 or 2%?
I think this one is, yes, this one is within 10% as well, yes. So
Okay.
plus or minus 10%. And he used the, a radiation dosimeter for the calculations.
And that's what stays in the room? Always like behind the lead barrier? at-
Sometimes
at
they'll
the
leave it in there,
clinics?
sometimes they'll take it with them. Yeah,
Okay.
it just depends. Alright, so we've come down to the last slide. So what does the flat field fan, what is the flat field phantom used for?
Flat field correction? Calibration? Correction?
Yep. So according to the ACR and the American Association of Physicists in Medicine, how often should the medical physicist perform QC testing on collimation? What is perhaps the most important patient protection characteristic of a radiographic imaging system?
The filtration.
Mhm. And what are the 3 instruments used to measure focal spot size?
Pinhole.
Pinhole.
Slit.
Is it star?
And slit.
See, y'all was paying attention. And the exposure time accuracy should be within what percentage of indicated time for exposure times greater than 10 milliseconds?
2%.
6 seconds to
10.
600 miles?
Isn't it 10? Plus or minus 10? No?
It's not 2%.
Mhm.
100? I think it's 10.
I think I heard it.
5. And
Mhm.
it's 6 seconds to 600 miles or something like that, right?
Then what was 10?
10 was the KVP.
There were 2 10s, right?
Radiation.
It's linearity.
10 was the exposure linearity.
Oh.
All right, y'all. So that's the end.
Miss